I want to draw a couple of broad distinctions at this juncture in order to frame up the information that follows. I think part of the challenge, actually a big part of the challenge, quite honestly, is trying to deal with the nomenclature. When we have 2 or 3 terms that mean the same thing, then it gets tough. So I'm going to try my best to head off some misunderstandings and minimize them if I can. So first we have a couple of ways that we do regression. First is the simultaneous way that we did last session, where we simply enter all predictors into one equation. All right, so simultaneous, one equation. We don't care about order of predictors going into the equation. There's just no order to things, always just one. It's very simple. I like it because it's elegant. But it's just one way that we do regression. And then there's the sequential way or hierarchical way. Sequential, I think, is a broader term than hierarchical. Generally, what we mean by hierarchical, I think, is when there is a theory-guided way, which I'm going to get into coming up here in a couple of minutes. But sequential is a broader term, and note that Keith calls hierarchical regression sequential. So just keep that in mind when you're reading his material. Authors aren't consistent in the use of these terms. But what hierarchical and sequential both mean is that predictors are added to a regression equation one or more at a time in sets or clusters of predictors. And actually what we're doing is running multiple regression equations. And so in the simultaneous way, again, we don't care about the order of entry of predictors, and it's just one equation. For the sequential one, there are going to be multiple equations, especially in the hierarchical way. We're going to run multiple ones of those, and then we're going to compare the R-squared across them to see if adding a predictor, an additional predictor, I should say, or set of additional predictors, is going to cause a significant bump or increase in R-squared. And we call this incremental variance explained, or incremental contribution to R squared. So whenever you hear these kinds of terms like incremental contribution to R-squared, or change in R-squared, or you hear semi-partial correlation, you hear, does this predictor explain variability in the DV above and beyond other predictors? All of these kinds of phrases are clues to you that a hierarchical regression is required to answer that research question. All right, so I'm going to show you an example of that way and all of these different phrases that can be used in research questions to give you an idea that this indeed is the appropriate analysis to run. So an example research question when we don't care about order, it's just one equation. For example, does my training workshop or my therapy method, maybe for clinical, does it predict a certain DV controlling for people's baseline levels? All right, so the baseline level is going to be a covariate or control variable. Those two are synonymous, covariate and control. We use them interchangeably. When we control for people's baseline, does our intervention does it still explain unique variability in the DV? And that's a great question to ask. It's very easy. I like it for that reason. But imagine that we have a little bit more complicated question where we want to know if our workshop or intervention, does it explain incremental variability in a DV above and beyond baseline levels? So we're going to have pre-workshop, some kind of pre-test, and then we have years of leadership experience. Let's say we have other things like, age, and we have, just because we're interested in it, we'll talk more about choice of control variables later, but imagine that your research question is, you have years of leadership experience, you have age, and other things. And in this case, we have a lot of controls there, right? And so the goal is going to be to understand the incremental variance change in R-squared when we add this intervention compared to when we just have these controls all in the equation just as a set together. All right, so we do this in blocks, we do this in kind of steps, sometimes we call it steps, and so I'm going to explain that all to you in great detail and go through some output in a bit. But moving on to the next slide in the deck, there's another distinction that's important, and that is there are two ways that we can do sequential regression, or I guess hierarchical, even though I don't like to use that term because that term feels more like a specific way that we do an ordered predictor method. But so here's where that gets challenging to explain. But basically what we're doing is we're going to break down this category into two separate ways. All right, so that's what this is about right here. All right, so when we care about order, when we're doing order of predictor entry and we're going to do it in a certain way, there are two ways to do it. The first way is with no guiding theory. So we are going to rely heavily on the algorithms that are underneath whatever stats platform we're using, whether it's R or M+ or whatever we're doing. And we're going to let those algorithms decide which combination of predictors to use to account for the most variability that we can in our outcome. All right, so there are several ways to do this. The three that I think have been used in the past most often are backward, forward, and stepwise. These, by the way, are not big data techniques. These are techniques that have been used before the big data algorithms were kind of established and popularized. All right, so and I think those, in fact, I know those big data techniques are much better than this method, and I'll explain why in a few minutes here. But just to give you an idea, even though we should never be using these, just a quick idea of what they are. So backward selection method. So order of predictor entry is, first we start off with all variables are in our regression model. And then the computer looks through those B weights and select the ones that are not significant and not contributing and just shouldn't be there, and it takes them out. And then the B weights all switch because the remaining B weights and their associated predictors are going to change because that predictor is out of the model. And then the computer looks again, the algorithm looks again and takes out the ones that are one that's contributing the least to, and it's not significant, not contributing to the variability explained in the DV, and it takes that one out. And it does this process over and over until all of the remaining predictors in the model are good. They're significant, they're contributing. Now the forward method is the opposite. So it begins with no variables in the regression equation. The computer looks through those predictors that are available and selects the one that contributes most to the R squared, basically. And so then it adds that one, and then based on how the predictors are doing that are remaining, it will select the next one that contributes unique variability to the DV. Given that that one's already in the model, it's going to choose the next best one until it's done. Okay, and that's the forward method. And then the stepwise is like a combination of the two of those. Basically starts with nothing in the model, and then the computer selects a predictor that contributes most to that DV, and it puts that in, and then it goes through the predictors again and selects the next best one, the next best one. But if an earlier one that it selected in the equation becomes non-significant, it pulls it out again. So it goes back and forth in this iterative process until it lands on the best, quote unquote, big air quotes here, the best model. And so you'd use those predictors to make decisions about people in the organization. Now, I would say that these techniques are generally used when you have a lot of cases in your data set, and especially not necessarily a lot of cases. We would hope there'd be a lot of cases, but if you have a lot of predictors and you just don't know which ones are contributing uniquely to the DV, and you have to make decisions about people. So an example would be something like in an organization you have all of these different predictors that you have collected, either archival data or otherwise, on applicants for a certain job. And you don't know which of these predictors is best to use. And so you're going to throw them all into the algorithm, so to speak, and let the algorithm decide by one of these methods. And so this is attempting, I think, in industry data. If you don't do some better big data techniques, and if you don't have a lot of cases in your data set, but you have a lot of predictors, you have access to many, many predictors, then I think sometimes the temptation is for the client to ask you to use one of these methods to figure out which set of predictors is going to be best to predict an outcome. Like for all these applicants, you have this data on them, their demographics, their skills, and you want to predict their future performance. I should have said that earlier. The DV is pretty important here. So you want to predict those applicants' future performance. And so you're going to run these 30 predictors through one of these methods to try to sort out which ones are doing the best. The problem with this is it capitalizes on type 1 error and it's not replicable in new samples. Big data takes care of that problem, and so the big data techniques are much better for this. Do not use these, not recommended, and I'll explain why coming up in much more detail. Now, there's a second way to do predictor entry, and that is theory guided. And Keith is even kind of, I think, pessimistic about this way as well. So you may have noticed that in the reading, Keith says, you know, don't even do the hierarchical method or the sequential method, I think he calls it. It's not usually helpful. However, the reason that I'm teaching it to you is so you know it exists, and you know that it's still widely used across both of our fields, I would say. And it is a simpler analysis than many of the ones you'll learn and be using for dissertation and things. But it is still widely used, I think, in industry as well, especially for medium-sized samples, which is generally what we're working with, for better or for worse, in this stat sequence and what we work with in academia. We don't have access to tens of thousands, hundreds of thousands of cases. Databases like that are usually for industry data. In academia, unless we have archival data, we usually don't have access to that kind of, and resources to collect those kinds of big samples. So we're working in the realm of medium-sized data sets, you know, N of anywhere from 150, I would say, is like a medium size, all the way up until like in the 800s or so. And once you get into the thousands, you can start to use some big data techniques and, what's the term? Some of the cross-validation techniques as well. Not going to go there now. So back to this. Theory-guided method is the second way to do if you're going to care about the order of entry of predictors. This second way is the way to do it. And so you have an underlying theory about which predictor should go first into the model, and the ones that are of focal interest to you that you think are really the ones that are either causally related to the DV or the best predictors. Usually that's going to be our intervention of some kind. It's going to be the most proximal, I guess, causal variable to the DV. We're going to put that into the last block of our sequence. And so putting in the covariates or control variables in the first block and letting those soak up variability in the DV that may be hiding the true variability of our intervention, whatever that is. And that is going to be the one that we think is most likely to be causally linked to the DV, and or the one that's just the most proximal and important predictor. That's what we're going to do with the theory-guided method. So we have this order of entry that we, instead of the computer, have selected, basically. The reason this is important is because when you throw a bunch of predictors into a model, there's no way to find the best set of predictors, even though these ways, the forward, the backward, stepwise, it would seem like they would get at the best set of predictors. They actually don't. I'll show you why in the next segment. So that's why the theory-guided one is so important, is unless you clearly say this is exploratory and you're going to validate it on a new sample, then it might be okay to do some of this mixed with theory, maybe. But most of the time we don't have the luxury of that. We don't have the luxury of many more data points to do that. So best to do theory guided, and throughout this class we're going to come back to this idea that's always better for us as the researchers to make decisions about which predictors go in the model and how, rather than relying on algorithms that are more blind to this process. All right, so again, just a quick summary. There are two methods of entry, basically. There's no order of entry. We have just one equation that we care about, and then there's this hierarchical or sequential, a specific order of things. Keith doesn't like this method too much, but we still teach it because I think it is appropriate to use it sometimes if we do it well, can be helpful for cross-validating and especially, and verifying on new samples. This can be good. If we have a strong causal theory, especially with whatever our focal variable is in the last block, we really care about this intervention, this technique to help people. Is it doing that? And of course, research methods is important here too. We need to have random assignment or some kind of design controls as well in order to strengthen the causality, because the stats part is just stats, and we'll talk more about that later, about this idea of the stats versus the methods, and how methods definitely contribute to causation inferences, whereas the stats do not. However, if you do have some strong, research methods, design controls that you're using, then this technique is better. It's a little bit more justified in my mind to use. All right, so there's no order, and then there's the specific order that we as the researcher, either we as the researcher specify, or that is done by algorithm. So both are in this category. And then here we're further dividing this category into the algorithm techniques, and then the ones where the researcher and theory decides how and when to enter those predictors.